Hello everyone. Just give me 5 minutes. I'm just having an internet glitch here. Just give me 5 minutes. Sorry for the interruption. Just give me 5 minutes. We'll continue the class. Just 5 minutes.
Okay.
Hello, everyone. I'm really sorry for all the inconvenience. So I'll just make up in today's class. So we were talking about development of electrode potential, and here for to understand what is electrode potential, we'll consider a metal M, and we will place the metal in its ionic solution, that is Mn plus. Now, in this case, what happens is that the metal contains both the metal ions and the electrons. So here both the phases, the metal and the solution, they contain metal ions Mn plus, but the activity of the Mn plus in the metal, it will be different from that in the solution. And since the activity is different, so what happens here is that the distribution of the metal ions in solution and inside the metal, it is different. So here how we will understand by taking the case of zinc. So here when we take a less active metal than zinc, let us say copper. So if we place a piece of copper in a solution of copper sulfate, then some of the copper ions, they get deposited on the copper metal, accepting the electrons from the metal solution and leaving the metal with a small delta positive charge and the solution with a small delta negative charge. Now in the second situation, suppose we take a more active metal, so here it will be the other way around. So that is few metals from the metal surface, they get into the solution phase, giving the metal a small delta negative charge, and the solution it acquires a small positive charge. So depending upon the nature of the metal that we are taking in solution, the nature of the charge will also vary. So here in the two cases, in these above cases, the positive and negative charges that is developed, it will be located at the surface of the metal solution phases. Now here the surface of the metal solution, we generally call them as the interface. So here this whole concept has been shown here in figure 1.1. As you look here into figure 1.1, in the first case, that is copper sulfate interface. So what happens here is we dip the copper inside the copper sulfate solution. Now the copper, it has delta positive charge, whereas the copper solution, it has the delta negative charge. Similarly, in the second case, that is in the zinc sulfate interface, what happens is that the zinc solution, it acquires the positive charge, delta positive charge, whereas the zinc, it acquires the delta negative charge. So now you can see in both the cases there is difference of charges. So one is positive along the interface, you can see there is a either positive charge and here is the negative charge. So two different charges are there, and because of this there is the development of the electrode potential. This difference in charge here in this case and here in the zinc case, it leads to the formation of a electrical double layer. So once this electrical double layer is formed, then we see a potential difference between the metal and the metal solution. So this potential difference is called as the electrode potential. So this is the very general understanding of what we call it as the electrode potential. Now electrode potential, this is very important in electroanalytical chemistry and the different techniques that are associated with electrode potential. Then comes how we should measure the electrode potential, because measurement of electrode potential is very important, and unfortunately there has been no direct method of measuring the electrode potential. But what we do to measure the electron potential, we have chosen a standard. So with reference to the standard, we measure the electrode potential of the solution that we are working with. So this reference electrode was first proposed by Nernst, and it is known as the standard hydrogen electrode, that is called as SHE, and it was arbitrarily given zero potential at all temperatures. So Nernst, we know he has developed many concepts in electrochemistry, and for particular measurement of electrode potential, a standard was set up. This standard was called as SHE, that is standard electrode potential, and its value is zero at all temperatures. And all the scientists and all the convention agrees to this zero value for the SHE, and it is the most common reference electrode that we ever come across. So whenever we want to measure the electrode potential, then what we do is we couple our sample with the that of the standard hydrogen electrode, and then the electromotive force of the resulting cell, it is measured, and then we find out the electrode potential of our sample. Then there is a very important concept here that is called as LJP, the liquid junction potentials. So here in liquid junction potentials, why they are important? They are important because they help in maintaining the sanctity, or they help in maintaining the overall, they how maintain the how, what should I say, the potential of the solution, or any disturbance that occurs during the measurement of the EMF, then they are all cancelled out by the liquid junction potential. So what is this? When two different electrolyte solutions, they are brought in contact, then an electrical potential difference, it arises at the zone of contact. So this potential difference, it is termed as liquid junction potential, or we call it as the diffusion potential, but mostly it is called as LJP, and we write it as EJ. So why this is caused? This is caused because of the, when we have a concentration gradient like this, the diffusion of the ions from higher concentration to lower concentration. So in such cases, when two different electrolytes are taken and there is a concentration gradient between the ions, then what happens is the migration or the diffusion of the ion, it occurs from higher concentration to lower concentration. So this is the movement or the mobility of such type of ions, it gives rise to the liquid junction potential. Now various types of liquid junction potentials are possible. Just one simple type has been shown here. Suppose we prepare an interface between two solutions which contain the same electrolyte but at different concentrations. Like for example, we prepare zero point 0.1 molar HCl and 0.01 molar HCl. So here HCl is the same electrolyte but their concentrations are different. So when these two solutions, that is the zero point 0.1 molar HCl and 0.01 molar HCl, they are made to come together, like they are brought together, then both the HCl and Cl minus ions here, if you look into figure 1.2, they move from left to right. Now why they move from left to right here in this direction? It is because on the left hand side the concentration of the HCl is higher, and on the right hand side the concentration of the HCl is lower. So because of this concentration gradient, both the H plus and Cl minus ions, they move from the zero point 0.1 molar HCl side towards the 0.01 molar HCl side. But what happens here is the hydrogen ions, they diffuse very rapidly in comparison to chloride ions. Now why is this? It is because of the size of the ions. Now since hydrogen ions, they are much smaller in sizes, and that is why they move rapidly towards the 0.01 molar HCl side. But the chloride ions, they move slowly. They also move, but the speed of the H plus ions is higher. So what happens here is, because of the H plus ions, they move rapidly, then there is a slight tendency for charge separation. With the right side here, the right side of the this part, it acquires a slight positive charge, and the left side here, that is this zero point 0.1 molar HCl part here, it acquires a delta negative charge here in this case. So this is how a liquid junction is developed, the potential is developed. So the liquid junction potentials, they may vary over a considerable range depending upon the conditions of the cells. Now these potentials can be minimized by using a salt bridge. So minimize this liquid junction potentials, we use salt bridges. For example, potassium and chloride, they have chloride ions, they have comparable mobilities. So salt bridge of aqueous potassium chloride with agar gel, they are used mostly to minimize liquid junction potential. So this is how a liquid junction potential, it arises, and by the use of salt bridges we can minimize the liquid junction potentials. Okay. So next, coming to electrochemical cells. So what are electrochemical cells? Then electrochemical cell, it consists of two metallic electrodes that are immersed in either the same electrolyte solution or in two different solutions that are in electrolytic contact. An electrochemical cell that can operate to convert chemical energy into electrical energy or vice versa, depending on the nature of the cellular reaction. So the most common acceptable electrochemical cell is what we call the conversion of the chemical energy into electrical energy, and it is called as the galvanic cell or the voltaic cell. So in alternative, the cell where which is non-spontaneous and here is forced to occur by passing through the current from the external source, it is called as the electrolytic cell. So what happens here is, first we will talk about galvanic cell. So what is a galvanic cell? So in a galvanic cell, the system, it contains two electrodes. So those are called as this here in figure 1.3. This is the whole representation of a galvanic cell, and one part of the galvanic cell that contains one half, or the half cell, we call it as the half cell. So here in one part we see zinc sulfate solution is present, and here in the right side part we see copper sulfate solution is present. So here in this galvanic cell is also called as a Daniell cell, and here it is shown here in figure 1.3. So the solutions of the two halves, that is the zinc sulfate solution and the copper sulfate solution, they are connected with a salt bridge. As you can see here, saturated KCl solution is taken, and this is the salt bridge. So the zinc strip, it is immersed in zinc sulfate, it contains the zinc electrode, and the copper strip, which is immersed in the copper sulfate solution, it constitutes the second half cell. So the combination of these cells, it gives the complete cell, and this cell was first proposed by Galvani, and hence the name comes from galvanic cell. Now when the circuit is closed, the cell operates spontaneously. Since copper has a higher positive potential than zinc, so electrons flow from zinc to copper in the outer circuit. Then the flow of electrons, when we know what is electric current. So when the electrons flow from one half cell to another, then electric current is generated. So here in this case, what happens, as the electrons, they flow from zinc to copper, then electric current is generated. So conventionally the flow of current is considered to be opposite to that of the electrons based on the concentration of the potential. So the cell reactions are the oxidation and reduction processes. So we have to find out in both of the half cells where oxidation is happening and where reduction is happening. So particularly in a galvanic cell, at the copper electrode, the copper ions are reduced where electrons are consumed, and this is known as cathode. At the zinc electrode, the electrons must be supplied by which is done by oxidation of zinc, and this part is called as the anode. So what do we know, that where mostly oxidation occurs, that part is, that electrode is the anode, and reduction happens at the cathode. So this is one generalized uh, part in electroanalytical chemistry. So here we have to always remember this. So here now when we want to write the total overall cell reaction, so it is always advisable that we write the anodic reaction at the, that is the negative electrode reaction, at the left hand side. That is for the zinc Zn2 plus, here it is written on the left hand side zinc, then Zn2 plus, activity of Zn2 plus. Here double bar, it indicates the salt bridge. And in the galvanic cell, since copper 2 plus to copper, that is the reduction reaction takes place here at the cathodic side, so it is always written on the right. So the single vertical bar, it represents the metal and metal solution interface, and the two vertical bars, they indicate the LJP. So if we want to write the half cell reactions, so for the half cell reactions we can write, looking at this reaction, we can write zinc present in solid form, it gets converted to Zn2 plus 2e. And suppose if we want to write out the half cell reaction for the cathodic reaction, here copper 2 plus, it accepts 2 electron and it forms copper S. So the overall reaction for the galvanic cell can be written as zinc plus Cu2 plus forming Zn2 plus Cu. So the EMF of a galvanic cell, it is the difference between the potentials of the two electrodes and the potential difference at the zone of contact of the two electrolyte systems. So thus, when there is no liquid junction potential, the EMF of the cell, or that is, it can be written as overall, this equation 1.7 is very important, and we will always write that overall EMF of a cell, that is E cell, it can be written as E right minus E left, that is E cathode, that is the electrode potential of the cathode minus electrode potential of the anode. So when we were talking of a galvanic cell, here we can write the cathode, and for the reaction, that is cathode, in cathode we can see the reaction that is occurring is Cu2 plus 2Cu. So here we can write the E cell is Cu2 plus 2Cu minus E of anode, that is EZn2 plus 2Zn. So the cell EMF is always positive, and therefore we write it in such a way it is always written, that is E cell is positive. So this is this equation 1.9. It is the general representation of the calculation of the EMF of a galvanic cell or a Daniell cell. So if the electrode half cell electrode potential of one electrode is known, then the overall E cell, it can be calculated. Then coming to the next part, that is an important part, and we call it as the Nernst equation. So the electrode potential of a redox couple, it varies with the concentrations of the reduced and oxidized forms of the couple. So Nernst equation, it talks of the equilibrium between the substances, between the between the EMF and the activities of the different ions that are involved in the electrochemical process. So first is the derivation of the Nernst equation. So from the first law of thermodynamics, we know that delta U is equal to Q plus W. So what is this delta U? This delta U is the change in internal energy of the system. W is the work done on the system, and here Q is what we call it as the heat absorbed in the system. Here we can write, since W is written as minus P del V, that is the work done, and W electrical, that is the electrical work. So we can write here as, and we know delta S, that is the entropy change, it can be written as Q by T. So Q becomes T del S. So we'll put the value of W and Q in equation 1.10, and we find out that delta U at constant Tp, it becomes T del S, that is the value of Q, minus P del V plus W electric. Then at constant pressure, we know that delta H is equal to del U plus P del V. And we also know the change in Gibbs free energy, that is del G is equal to del H minus T del S. So when we combine both these equations, we get del G is equal to del U plus P del V minus T del S. So when overall combining all the equations, we find out that delta G at constant T and P is equal to W electric. That is, the Gibbs free energy at constant temperature and pressure is equal to the amount of electrical work done by a system. So this is what we got this in equation 1.17. Now we will apply this concept to a galvanic cell. So we will consider a galvanic cell which has two terminals, and the potential difference is E, and a charge of Q, it moves through the circuit. So for this case, galvanic cell, the work done, that is W electrical, is equal to E into Q. Now we know that Q is equal to NF. So N is the number of moles and F is the Faraday constant. So here this we have studied just now, that is the from the laws of electrochemistry. Then we combine both these equations and we see that delta G is equal to minus NFE. So this is also another important observation, that delta G is equal to minus NFE. Now again we will consider a chemical reaction, that is A plus B forming P plus R with the respective the small ABPR, it represents the number of moles involved in the reaction. So for this reaction, the change in free energy is given as, we know this, it is given as del G is equal to del G0 plus RT into ln of concentration of the products by concentration of the, by activity of the products by activity of the reactants. And here capital R is the gas constant, T is the temperature in the Kelvin scale, and delta G0, it is the Gibbs free energy of the substance in standard state. So now here we can write delta G0 is equal to minus NFE0. So overall we can write minus NFE is equal to minus NFE0 plus RT ln of the activity of the concentrations. Now if we divide both the sides by minus NF, we find out that E is equal to E0 minus RT by NF ln of activity of the products upon activity of the reactants. So by changing the is this minus sign to positive sign, we can write it as E is equal to E0 plus RT by NF ln of activity of the reactants by activity of products. And now substituting the value this here ln, we can convert it to log, so that is it becomes 2.303 RTNF by the whole process. Now we know the value, numerical value of R, that is the universal gas constant, it is constant. The value of F we know, and putting T is equal to 290 K. This overall equation now takes up this formula, that is E is equal to E0 plus 0.0591 by N into log of concentration of the reactants by concentration of the products. Now this equation, that is equation 1.29, it is the most accepted form of Nernst equation that we use in analytical chemistry or in chemistry. So this equation plays a very important role in determining the EMF or in knowing the EMF of our substances. So now we will use this equation. So one common example has been given. So we'll consider a simple electrode, that is a half cell with a metal cation equilibrium. That is, we'll consider a half cell of this type where M is the metal. It takes up n number of electrons to form the metal M at 25 degrees centigrade. So for this equation, the Nernst equation can be written as E is equal to E0 plus 0.59 by N into log of concentration of Mn plus. Here the concentration of the pure metal will always be neglected because it is always equal to 1. Then, so here for a more general form of this reaction, the Nernst equation, it can be written as E is equal to E0 plus 0.0591 by N into log of, we will start with the reactant side, that is O raised to the power X, concentration of W raised to the power M. Similarly, divided by the product is R and Z, so that is the concentration of R raised to the power Y and the concentration of Z, that is raised to the power Z. So this is how we write a Nernst equation for complex reactions. Now when we consider a galvanic cell, so but for a particular galvanic cell, the Nernst equation can be written as E cell is equal to E0 cell plus 0.0591 by 2. Now where does this 2 comes from? This 2 comes from the number of electrons that is involved in the overall reaction of the galvanic cell, and this is log of copper 2 plus concentration by zinc 2 plus concentration. Now this equation, it can be used to calculate the EMF of the galvanic cell. Now let us consider the following reaction. Here in this reaction, if you see, MnO4 minus plus 8H plus 5E, it forms Mn2 plus 4H2O. So if we want to calculate the EMF of this cell, so we can write it as E is equal to E0 minus 0.0591 by 5. So why this 5 is taken? So here 5 is taken because five number of electrons are involved here. Concentration of Mn2 plus and the concentration of MnO4 minus and concentration of H plus raised to the power 8. So this is how we can apply the nonce equation in calculating the cell potential. Then sorry, the EMF. Then coming to the cell potential. So the potential difference between two cells that is connected properly to form a galvanic cell when no cell current flows through it, it is called as the EMF or the cell potential. Now, when the potential, if we have two cells, they are in connection with each other, but there is no flow of current through the system, then at that system, at particular time for that system, the overall EMF of the cell potential, it is called as the cell potential. Now, when current flows through the system, then the EMF changes. So, when as you allow current to pass through the system, then the methods of measurement of cell EMF, it results the voltage values lower than the cell potential because the passage of current allows appropriate reactions to occur, hence changing the concentration of the solutions and lowering potential difference between the electrodes. So there has been no method for measurement of potential. Is we know that there is no direct method of measurement of potential is possible, then it is apparent that when what we measure is EMF of the cell at a insignificant current flow or a close approximate at the cell potential. So in actual practice, cell potential is measured by a null point method with a potentiometer which involves balancing the cell output EMF against an identical and measured externally applied voltage under an insignificant current flow through the cell. The cell potential can also be calculated on a theoretical basis using the Nernst equation. This is the most commonly followed method. These calculations are done in two ways. In first way, we calculate the potentials of the individual electrode using the Nernst equation. That is, first we calculate the half cell electrode, and it involves a separate reaction which is considered in isolation. The higher value of the reduction potential, that is more positive values of the potential, it indicates that it will act as the cathode and will written on the right side, whereas the less positive value, it indicates that it is an anode and it is written on the left side. So how do we write it? We can write it as E cell is equal to E right minus E left. In other way, we can calculate E cell in a consolidated manner by calculating the E0 cell. So what is the E0 cell? That is the EMF of the cell in its standard state. So then then again we will subtract this and then we will apply the Nernst equation and we can find out. So in both the ways, we have to first calculate the half cell reactions and then we write out then we can find out the E cell. So one example has been shown here. So if you look at the first example, here a cell is set up as follows. The cell is the zinc 2 plus. The activity of zinc 2 plus is A is equal to 5 into 10 to the power minus 3. Then copper 2 plus, the activity of copper 2 plus is A is equal to 2 into 10 to the power minus 2 to copper. Then the standard potentials are here. It has been provided to you that E0 for copper 2 plus to copper is 0.337 volt and E0 for Zn2 plus to Zn is equal to minus 0.763 volt. So how we will calculate? So first is it has been given that you calculate the cell potential, indicate the polarity of the electrodes and the direction of the spontaneous reaction. So first we will write out the overall cell reactions. So here it has been given that zinc 2 plus to 2E it forms Zn, copper 2 plus 2E it forms copper. So here the E0 has been provided. Then the individual first, for this case we will write out the individual electrode potential by using the Nernst equation. So first we will apply for Cu2 plus to Cu. So here it becomes E0 Cu2 plus to Cu plus 0.0591 by 2. So why 2? Because 2 electrons are involved here into log of activity of copper 2 plus. Here the value has been given as 2 into 10 to the power minus 2. So you apply this and we get the value to be this. Similarly, for EZn2 plus 2Zn, so it is calculated by using Nernst equation. Again, that is given as E0 Zn2 plus 2Zn plus 0.059 by 2 Y2, two electrons are involved, and the log of activity of AZN2 plus. So here AZN2 plus is given as 5 into 10 to the power minus 3. So we get this. Now here the half cell will overall reaction. We know this is the overall reaction, and finally putting all the values we can calculate the value to be this. But this whole method, it can be done in a very simplified expression of the non-stick equation, that is E0 cell plus 0.0591 by 2 into log of activity of copper by activity of zinc. You directly put the value and then we get the value to be the overall cell potential can be calculated. So this is how non-stick equation is useful in calculating the overall E cell. So another question has been given of the same type. Now coming to classification and overview of electroanalytical methods. So although there are various types of electrochemical methods, all of them are based on a rather limited number of percepts. The general classification is based on the particular electrical property or the properties measured by keeping the other quantities constant and the mode of transport, that is either diffusion, convection or migration. So there are basically these techniques, they have been divided into two types on the basis of procedures adopted for analytical determination. The first is the methods in which little or no chemical transformation occurs, and the measurement of an electrical quantity, it gives a direct measure of concentration, such as example is your direct potentiometry. And the second type, it involves the method that are based on the titration procedures. So here what happens, where a analyte, it undergoes stoichiometric transformations and they are determined by titration. So these methods are most commonly like potentiometric titration, amperometric titration, etc. We will gradually discuss this process in details. So first we will start with what is potentiometry. So we'll just take a break of 5 minutes and then again resume this class. Okay, so we'll start with direct potentiometry. So first we'll understand what is potentiometry. So potentiometry, it involves the measurement of the potential when current flow is zero. So analytical use of this technique is done in two ways. First, it is called as the the direct potentiometry. In the other technique, that is the indirect potentiometry, we usually call it as potentiometric titration. So here in direct potentiometry, the single measurement of potential and the Nernst equation, it is used to calculate the cell potential and the concentration of the analyte. Whereas in potentiometric titration, a set of measured potential, we have a set of measured potential. Then from the equivalent point of the titration curve, we calculate the actual potential which induces the change in the sample. So we'll discuss one by one. So first, coming to direct potentiometry. So here in direct potentiometry, here we measure the potential difference between two electrodes that are immersed in a solution and connecting the cell so formed to measure the voltage. So here directly what happens is, when two electrodes that are dipped in a solution and they are connected, so what happens, the cell that is formed, so and it is connected to a potentiometer, and because there is a potential difference between these two electrodes, the difference is measured, and this is what we call it as the, when two half cells are connected, then we call it as the galvanic cell. Then the net cell reaction, it can be calculated by using the process of the Nernst reaction, and one of the electrodes is chosen such that its potential is invariant, and it is called as the reference electrode. The potential of the other electrode is a function of the concentration of the species involved through the, and it is calculated through the Nernst equation, and it is called as the indicator electrode. So under these conditions, the cell EMF is given as E is cell is equal to E of the indicator electrode and the E minus the E of the reference electrode plus EJ, here it is the liquid junction potential that is developed at the two electrolyte surface. So concentration of the solution, here it is determined by a single measurement of the cell potential by applying the Nernst equation, or we can draw the calibration curve of E versus log of concentration of the species, and then we can calculate the overall E. So now it is important that the indicator electrode, it should respond selectively to the species of analytical significance, and this practical requirement has stimulated the development of many types of indicator electrodes. A common type of indicator electrode for potential measurements, it consists of a metal in contact with a solution containing its own ions. So such an electrodes, we call it, has been used, that is called as the metal ion or the metal redox couple. So an inert metal such as platinum that is immersed in a solution containing an appropriate redox couple such as Fe3 plus or Fe2 plus, it can also be used to form an indicator electrode. Several electrodes with good selectivity for specifications, they are based on the development of potential across the membrane. So electrodes of such type, we call them as ion selective electrodes. So the glass electrode is the most commonly used for pH measurements. It is an ion selective electrode. The stability and wide pH range of this conventional glass electrode makes pH determination an important tool in analytical chemistry. The instrument used, which we call it as the pH meter, it measures the potential of the glass electrode with reference to the external reference electrode, and it displays the output digitally. So here this part, it will be later discussed in the next unit. Then coming to potentiometric titrations, this is indirect potentiometry, but we do not use the term, we call it as potentiometric titrations. So here, as the name implies, so titrations are involved. So potentiometric titration, it has been this potentiometry, most, it is the most common application of potentiometry has been by the process of potentiometric titrations. So what we do in these titrations, So here in these titrations, the potential between appropriate indicator and reference electrode, it is immersed in the sample. It is monitored during the titration. So we do a series of titrations. So this titration, they can be performed manually, or we have the titration equipment. Now the cell potential, it is plotted as a function of the volume of the titrant that is consumed during the titration process. So to understand this, let us consider the redox titration R1 plus O2 forming O1 plus R2. Now here, if this above reaction is stoichiometric, then we can plot the cell potential against the volume of the titrant that is consumed. Since the potential of the reference electrode remains constant, the variations of the potential of the indicator electrode, they are followed during the titration, and the endpoint is determined from the resulting titration curve. Now, here the indicator electrode, it should be such that it responds to a component in the titration reaction. The amount of reactant is calculated from the volume of the titrant that is required to reach the equivalence point, and the equivalence point is detected when we see a very drastic change in potential. And we can, the point at which the very drastic change occurs is termed as the equivalence potential. So it is determined by three procedures: by the tangential method, first derivative method, and the second derivative method. So this is just a general introduction to potentiometric titration. This has been elaborated in the next chapter. Then coming to voltammetry. So like potentiometry is a process, voltammetry is also another electroanalytical process. So what happens here is, in voltammetry, an electroactive species, it is either oxidized or reduced only at the surface layer of the indicator electrode in an electrolytic cell. The resulting current due to the electron transfer process is measured as a function of applied potential. Such electrolysis is carried out under controlled conditions of diffusion. So in diffusion layer, electrolysis methods, only a thin layer of solution immediately adjacent to the electrode, it undergoes electrolysis. In these methods, the electrical variable is related to the concentration of the bulk, and usually the time of electrolysis is very short. In voltammetry, we study the relationship between current and electrode potential, and we apply them to different chemical analysis. So the current potential characteristics are studied. That is, here it is shown in figure 1.4. Here the voltage applied to the cell C, this overall cell C, it is adjusted by means of the potentiometer P. Here it is present, and the current through which the cell is read by the galvanometer G. So here we have the galvanometer and the potentiometer, which shows the EMF of the voltage applied to the cell. So voltammetric curves, they are known as current volt curves or current potential curves. They are also called as IE curves depending on the polarization of the indicator electrode. So whenever we come across the term IE curve, that is the current potential curve, so we should understand that these are all voltammetric curves. Then coming to polarography. So polarography is also another electroanalytical technique, and various types of electrode cells, they can be used in voltammetry. So but one of them that is a very important among the various types of electrode, one of them is very interesting, and that we call it as the dropping mercury electrode, or we call it as DME. It is particularly useful, and the corresponding voltammetric method is called as your polarography. So why polarography has been typically classified as another class, it is because they use this DME. So DME is the excuse me. So DME is the dropping mercury electrode. Whenever we use DME, then we call them as polarography. So it was first originated in Prague. The dropping mercury electrode consists of a capillary that is connected to the mercury reservoir. The bore of the capillary, the length of the capillary, and the head of the mercury, they have been adjusted in such a way that a drop is dislodged every 2 to 6 seconds. No, and a platinum wire is immersed in the mercury reservoir, and the DME is coupled with unpolarized electrode. So polarography, it consists of electrolyzing a solution of an electroactive substance between a DME cathode and reference electrode anode. The area of the anode is large correspondingly, so that it may be regarded as unpolarized, and the potential of such electrode remains fairly constant. The current potential characteristics, it can be studied with the type of an apparatus. Here it is shown in figure 1.5. This is a manual polarographic circuit, and here the in a simple manner it has been shown here. The voltage here, it is applied to cell C, which is adjusted by means of a potentiometer, and it reads on a galvanometer G, and this is the saturated galvanil electrode. Here you can see this is the mercury, and this is the dropping mercury electrode, where a drop is lodged here at this point. So here, on applying the current between two electrodes and increasing its value in a stepwise manner, the following processes takes place. So what happens first is only a small current flows. It is called as the residual current. So this continues until the decomposition potential of the species is reached. At this point, the following reaction take place. That is, the Mn plus Me, it forms the M of the mercury. So after the residual current is reached its limit, there is a steep rise is observed, and it will continue to rise with increasing potential till it reaches a limiting value. So here you can see, for first time we have a residual current, then it increases, it reaches a maximum value, and that is called as your limiting current. So here in figure 1.6 you can see the IE curve for a polarogram. So the conditions here are set such that the diffusion is the main process of mass transfer. This can be done by minimizing convection and migration. The limiting current is known as the diffusion current, and we write it as ID. So the factors that affect the diffusion current, they were examined by D. Ilkovip, and here it is given by the Ilkovip equation, that is ID, the limiting current, it is given as 708 Nm to the power 2 by 3, capital D into half to the power half, T to the power 1 by 6 into C. So, and what are these parameters that have been used in the Ilkovip current equation? So, ID is the diffusion current, small n is the number of electrons that is used in the consumption of reduction of the Mn plus, capital D is the diffusion coefficient, small m is the rate of flow of mercury, T is the time, C is the concentration, and what is this 708? It is the combination of different constants and conversion factors that have been used in this equation. Now, when we look into this equation 1.44, we see a very important observation, that is, from this equation we can see the diffusion current, that is ID, is directly proportional to C, or we can write that ID is equal to Kc. So here K can be evaluated by noting the current of the standard solution. So here diffusion current is always directly proportional to the concentration of the Mn plus ions that is present in the solution. So this diffusion current will also be discussed in details in other units. Now coming to amperometry. So in amperometry, particularly amperometric titrations, they have been named after ampere, and in such amperometry, it is based on the measurement of current when the voltage across the electrodes, it is kept constant. That is, in amperometric titrations, the current passes through the cell at a particular voltage is measured as a function of the volume. So by far the application of amperometry remains in amperometric, mostly in amperometric titrations. So amperometric titrations, they are more accurate than volumetric methods, because this titration they can be formed even when the substance being determined is not reactive. Since an equally satisfactory equivalent point, it can be located much easier. So the equivalence point, it is obtained by extrapolation of the linear segments to their intersection. So either this point can be done by a DME, solid state platinum electrode, or a rotating platinum electrode, or any other electrode. So further details have been provided in other units. Then coming to electrogravimetry and coulometry. These are the various classes of electroanalytical techniques. So what is this electrogravimetry? Now Faraday's laws of electricity, it gives a direct proportion between quantity of electricity and the amount of substance that is consumed or obtained after oxidation and reduction taking place when a current is passed for a sufficient period through an electrochemical cell. Two electroanalytical techniques are based on this. One is the electrogravimetry and the other is the coulometry. So both these are bulk electrolytic techniques. So what happens is electrogravimetry. So whenever the word gravimetry is present, we should understand that it deals with the weight of the substance. So electrogravimetry is the oldest electroanalytical technique. It involves the controlled potential reduction of a solution of a metal salt, which is continued till the current falls near to zero. Thus, electrolysis is used as a means of chemical transformation. The product of analysis is weighed after as a deposit on the electrodes after the reaction is over. So, the increase in weight of the electrode is measured, and then we can calculate the the changes that has occurred during the electrochemical process. This method is very simple. The appropriate electrode potential we have to know, and just by applying the non-stick equation we can calculate. So then comes the coulometry. So in the bulk electrolysis method, when the amount of the constituent to be determined is not weighed but calculated by measuring the quantity of electricity and making use of Faraday's law, then the technique is called as coulometry. So coulometry is derived from the word coulomb, that deals with the quantity of the current. So in primary coulometric analysis, the substances being determined, they may directly undergo reaction at one of the electrodes. In secondary coulometric analysis, the substances being determined, they react in solution with another substances and they get generated at the electrode reaction. So further in coulometric analysis, which consider the reactions proceeding with 100% current efficiency, so the quantity of the species reacted can be calculated from Faraday's law. So now we know that from Faraday's law, that here N is equal to Q by NF. So by using Faraday's law, we can calculate the amount, the value of Q can be calculated. So coulometry has been classified into two types. One is potentiostatic coulometry and the other is amperostatic coulometry. So potentiostatic coulometry, here in this coulometry at constant potential, the potential of the working electrode, it is maintained at a constant level, so that only the analyte it gets quantitatively oxidized or reduced. There is no involvement of the less reactive species. Here the current is initially high but decreases exponentially with time and approaches zero at a time that is required to for the completion of the reaction. So here Q has been shown, the calculation has been shown here in 1.7, figure 1.7. This is the current versus time plot, and how to calculate Q is equal to 0 to T into I dt. So then coming to amperostatic coulometry. So amperostatic coulometric means here the current is constant. So the current in a coulometric titration, it is carefully maintained at a constant and an accurately known level by means of an amperostat. So the essential requirement is 100% current efficiency. It has to be there. That means the current has to be maintained at zero. So in these titrations, the titrant is generated at one of the electrodes. The reaction, it takes place on the same electrode or on the other electrode. So the reagent that we use can also, it can be generated externally, which removes the interferences. Mostly the cell which mainly has been used to generate H plus OH plus ions. Then coming to conductometry. So now coming to conductometry. So here the methods which involve the charge transport by the ions in solution, they are called as conductometric methods. So under these conditions, the resistance of the cell depends upon the velocity of the ions and on the number of migrating ions. It is observed that the conductance of all cells, which is the reciprocal of the resistance, is approximately proportional to the concentration of the electrolyte. The major advantage of this technique is that it is simple and it has good sensitivity. However, the selectivity is poor because the conductance of the cell depends on the concentration of all the ionic species that are present in solution. So the principle of the Wheatstone bridge that we know, it can be used to measure the conductance of the solutions. However, the solution following considerations, we also need to keep them in mind. So first is, since we use a direct current, it would polarize the electrode in a conductivity cell by electrolyzing the solution. So to avoid the polarization, and alternating current is mostly used. A suitable conductivity cell with two plating electrodes dipped in the solution is placed in one end of the bridge and in one place of a unknown resistor. Since the cell also acts like small capacitor, therefore to balance its capacitive reactance, a variable capacitor must always be present. So these are some of the conditions that we need to know while working with a conductometer. So here in conventional conductometric methods, an AC frequency of 50 to 1000 CPS, that is cycle per second, is used. This procedure can be modified by using higher frequencies, and these methods are called as high frequency methods. In these methods, the electrodes, they are not in immediate contact with the immediate contact of the solution, but they are separated from the solution. So as a result, the cell, it acts as a whole composite of capacitors and resistors. The response of the cell, it depends on the frequency, conductance, capacitance, dielectric constant, and the cell geometry. So then coming to classification and relationships of electroanalytical methods. So here, uh, as we have seen, there are different types of electroanalytical methods for different purposes. Now, some of these methods, they differ in very few aspects, but often the applicability of these processes are huge. So for the purpose of classification, methods can be divided into interfacial methods and bulk methods. The former, they are based upon the phenomena that occur at the interface, whereas the bulk methods are the processes that occur at the bulk level. So here interfacial methods can be divided into major subgroups. Here we can see it has been divided into two major subgroups. One is the static method and another is the dynamic method. The bulk methods, they have been also divided into two subgroups. One is the conductometric method and the other is the conductometric titration method. Now, if you look into the static methods, here it has further divided into two classes. One is potentiometry, the other is potentiometric titration. The dynamic methods are also classified into two types, controlled potential and the other is by constant current. This constant controlled potential is consists of four subclasses. So one is constant electrode potential, one is voltammetry, one is the amperometric titration, the other is gravimetry. The constant current method is also divided into two types, further divided into two subgroups. One is the coulometric titration and the other is the electrogravimetric titration. So here this is the overall representation or the relationship between different electroanalytical methods. So with this, we finished the first unit on introduction and the understanding of some of the basic concepts of electroanalytical chemistry. So now we will start with the details of each of the electroanalytical techniques that we have come across. So first is the potentiometry. Now, first we'll just recall what is potential difference. So here we know the application of the Nernst equation, E is equal to E0 minus 0.0591 by NF, ln of activity of the reactants by activity of the products. So we know the application of Nernst equation. Then we'll start with the measurement of potential. So as we have talked about, direct measurement of potential is very difficult, so we use an indirect method or a standard by using a standard. So now we will discuss in details how we can measure the potential. So the electromotive force that is developed by a galvanic cell, it cannot be measured accurately by simply placing a DC voltmeter across the electrode. So here, because current is drawn from a cell, variations are bound to happen, so which will lead to a change in the cell voltage. So an additional factor is the development of a ohmic potential due to internal resistance. So this opposes the potential. So potentiometer basically meets this type of specification, and here it has been shown in figure 2.1 how a potentiometer, laboratory potentiometer, it works out. So here, if we look into the figure 2.1, that represents the circuit diagram for a general laboratory potentiometer. The working battery with potential EB, it is connected to terminals of a linear voltage divider. Here is A and here we have B. Where is B? Here it is B. Then what happens here is the electrical resistance, that is RAC, from one, that is from point A to point C. So it is directly proportional to the length of the resistor, and in the simplest form the divider consists of a uniform resistance wire that is mounted on a meter. So here, what is the basic principle for this working lab potentiometer is that the current flows continuously through the point AB. It causes a potential drop between A and B. So from Ohm's law, we can write E is equal to I into resistance of R in, of AB. The current passing through AC is also given as E of AC is equal to I into R of AC. Now we know that resistance along a resistors is linear in nature. So we can write EAB is equal to K into I of AB. EAC is equal to K into I of AC. So now dividing and rearranging this equation, we find that E of AC is equal to E of AB into length of the AC by length of AB. So now here are three possibilities if the potential divider is adjusted to a position of EAC and K is pressed. So two of these are when EAC is greater than E of unknown potential or E of standard potential, then the electrons will be forced to flow from right to left through the unknown cell and the direction will be reversed. The third case is when if we have the E of AC is equal to the unknown potential, then no current flows through the galvanometer. However, the electrons will continue to flow from A to B under these circumstances. Now, if in general, in practice, what we do, if the key is tapped and C is moved, then there is no current flows. So with the cell, standard cell and unknown cell in the circuit, here we can write EX, that is the unknown potential, it is given as EACX, that is E of AB, into the length of ACX by AB. So here, by using this equation or by arranging the above equation, we can write the unknown potential of the cell is equal to ES into ACX by ACS. So here, this is how we can calculate the unknown cell potential. Then coming to standard cell. So standard cell is, we have seen the most commonly used standard cell is the Western cell, or we call it as the Western cadmium cell. Here it has been shown in figure 2.2. As you can see here in figure 2.2 is the Western cadmium cell. So Western, this is what we you have to remember, because this is one of the most this has very important like Wheatstone bridge, this is an important concept here. So first is the Western cell. What we do, so here, so for this Western cell, It is depicted in figure 2.2 and it is represented by equation 2.13, that is cadmium in cadmium sulfate dot 8 by 3 water, mercury sulfate, mercury. So here the two half cell reactions that occur in these cells are cadmium to cadmium 2 plus plus mercury plus 2e, then mercurous 2 plus to 2e forming mercury. So the overall cell reaction is written here, given as such. The potential of this western cell is 1.0183 volt at 20 degrees centigrade. Now this is temperature dependent and it is given highly dependent on temperature. Now in actual practice there are very small variations in the way in the EMF of western cells supplied by different manufacturers, and it is essential to use the exact value that is quoted by the manufacturer. So while using it, then a western cell of known EMF, which is always kept reversed for calibration purposes. So before using this, calibration is needed. At no time, current can be drawn for longer times from a western cell. So here is a typical design. Here it has been shown in figure 2.2. The potential measurement using the potentiometer, it is quite suitable if the galvanic cell having internal resistance is less than 10 to the power 3 ohm. So now digital voltmeters that we see in markets as pH meters or ion meters, they are mostly they work on this principle. Then coming to direct potentiometry. So potentiometric of methods, they can be grouped into direct reading method, that is, or direct potentiometric method, or potentiometric titration. So the direct potentiometric method is the method which makes use of the single measured electrode potential to determine the activity of the ion. This method, it is widely used for the determination of the pH, that is mostly using the SHE, that is the standard hydrogen electrode. In all the electroanalytical methods, two electrodes are required. The potential of one is known and it is completely independent of the composition of the solution, that it is called as the reference electrode, and the second is our sample electrode, or what we call it as the, it is dependent and it is called as the indicator electrode. So for direct potentiometric measurements, the potential of the cell, it can be expressed as E cell is equal to E indicator minus E reference plus EJ, where EJ is the junction potential. Let us consider an indicator electrode whose potential vary with cation activities. Here it has been given by equation 2.1, that is E indicator is equal to E0 indicator plus 0.0591 by N into log of concentration of AM plus. Now we substitute this equation 2.17 in equation 2.16. So we get this equation in 2.18. Overall arrangement of this equation, it gives us that the P of A, where P of M is the for the cation, it gives us minus N E cell minus K by 0.091. P of A, that is the A is the activity of the anion, and here it can be given by this equation. So here all this is how we can calculate. Then all direct potentiometric methods, they are based on these two equations. Now these two equations can be simplified in terms of equation 2.22 and 2.23, that is E cell is equal to K minus 0.0591 by N into P of M, and here E cell is equal to K plus 0.0591 by N into P of A. So now using these two equations, we can determine the concentration of ions or cations that are present in terms of PM and PDN. So here in electrode calibration method, the K value, it is determined by measuring the E cell for one or more standard solution known for PM or PA. So calibration plot is important because when we calibrate the instrument, then it helps in the determination of the K value that is essential for knowing the PM or the PA. So then coming to reference electrodes. So why are reference electrode? They are important because we know reference electrode is the one which has where the potential, what it is fixed in comparison to which does not change. It is independent of the solution that we have taken. So the potential of the electrode, so whenever we select a reference electrode, we need to remember some important points. The first point is the potential of this electrode, it should remain constant even when current pass through it. The potential, it should be reproducible. The electrode should be easily prepared from readily available materials. The potential of the electrode should not change with temperature, and it should be cheap. Then coming to hydrogen electrode. So what is an hydrogen electrode? This is the most commonly used reference electrode, that is SHE, or the standard hydrogen electrode. So we know that the standard electrode potential, they are mostly quoted with reference to the SHE, so which is fixed at 0 under all conditions of uh, fixed conditions of, that is H2S gas at 1 atmospheric pressure. The hydrogen ions of the solution and the gaseous hydrogen, they are taken in equilibrium, and in a platinum electrode it is coated with a thin film of platinum black. Here figure 2.4, you can see the common design of hydrogen electrode, that is the SHE. The platinum electrode, it is cleaned with hot chromic acid and it is thoroughly washed with distilled water. Then it is electrolytically plated from a solution of chloroplatinic acid with platinum foil as the anode. It is important that a thin jet black deposit is formed, and the thick deposits, they are not satisfactory for use as hydrogen electrodes. After platinizing, the electrode is to be freed from the traces of chlorine. The most convenient source of hydrogen is the compressed gas available in the market in cylinders. The gas is purified by passing through all glass bottles, such as containing zero point 0.2 molar KMnO4, pyrogalol, dilute H2SO4, and distilled water. So here, figure 2.4, it shows the typical arrangement of the commonly used hydrogen glass electrodes. So even though the hydrogen electrode is first and primary reference electrode, other standard electrodes have also been developed, and for comparison, so hydrogen electrode is convenient for use in practical lab because it has the following problems that are associated with using a hydrogen electrode. That is, it requires a large gas cylinder, hydrogen and air mixture is highly explosive, and the catalyst that is used here, it can be easily poisoned. So to avoid all these limitations of hydrogen electrode, other reference electrode has also been used. First is the calomel electrode. There are calomel electrodes. The calomel electrode and silver chloride electrode, they are also commonly used as reference electrodes. The calomel electrode is mostly used electrode because of its ease of preparation and constant potential. So calomel hapsel is one in which mercury and calomel, they are covered with aqueous KCl solution of definite concentration. If the KCl solution is saturated with the calomel, the electrode is called as saturated calomel electrode here. So what happens here? If we take KCl solution, not but saturated KCl solution, then we call it as the saturated calomel electrode. The electrode potential of such electrode is plus 0.24 volt at 25 degrees centigrade, and it has been determined against the SHE. So if the KCl solution is exactly zero point 0.1 molar that we have taken, then the potential becomes 0.28 volts, and this is called as the SCE, that is the standard calomel electrode. The electrode potential of different types of calomel electrodes, here it has been shown here in table 2.1. The Hapsel reactions for this calomel electrode, here it has been shown here. Hg2 plus 2e forming 2Hg. It may be, we know that mercury is a dimeric species. So now if we apply Nernst equation, we get E is equal to E0 minus 0.0591 by 2 log of 1 by Hg2 2 plus. Now here Hg2 plus, rearranging all the equation, we can find that E is equal to E0 minus 0.059 by 2 log of chloride ion by solubility product of KSP. So calomel electrode, it can be fabricated in different shapes and sizes. Some of the commonly used calomel electrode, they have been shown in figure 2.5. So here in figure 2.5, now the first one, the 2.5a, it is a laboratory made saturated calomel reference electrode, and the third is the commercial calomel electrode. So here it should be emphasized that the potential of an electrode, it does not depend on the size. Likewise, the liquid junction potential between the test solution and KCl solution, it may be physically established in various ways. Sometimes it involves an agar plug or a sintered glass, and sometimes a pinhole. Although the contamination from calomel electrodes is inconsequential, it must be remembered that even a small amount of KCl might go into the solution. So for special purpose, modification of the electrode, calomel electrode, it is preferred. It is thus, if it is necessary to avoid KCl K plus ions, the electrode may be prepared from Na plus ions. So now coming to silver electrodes, that is AgCl electrodes. So here in AgCl electrodes, it is similar to the one that is we have talked about, that is calomel electrode. So AgCl, it consists of a silver wire or a silver plated platinum wire that is coated with a thin layer of silver chloride. So it is represented as AgCl, KCl to Ag, and the Hapsel reaction is given as AgCl plus E forming Ag plus Cl minus. Normally, this reaction is prepared with saturated KCl and its potential is 0.199 volt at 25 degree when we measured at the SHE. This electrode can be constructed easily, and here in figure 2.6 a silver chloride reference electrode has been shown. The electrode is contained in a glass tube fitted with a 10 fitted glass or porous plug. A layer of agar gel and KCl is placed on top of the disc to prevent the loss of solution. A portion of the hot suspension is poured into the tube, which on cooling it solidifies to a gel. The layer of solid KCl is placed on the gel and the tube is filled with saturated KCl. So a drop or 2.1 AgNO3 is added and the heavy gauge of silver wire is inserted into the solution. Then coming to indicator electrodes. So an indicator electrode of a cell is one whose potential is dependent on the activity of a particular species whose concentration is to be determined. Several metals like silver, copper, mercury, lead and cadmium that show reversible half reactions, they are used for the construction of indicator electrodes. So among the metals like nickel, cobalt, tungsten, they do not give reproducible potential, and that is why they are not used as indicator electrodes. So usually these metal electrodes, they are constructed from coils of wire, flat metal, metal plates or buttons. Large surface area is preferable because of rapid attainment of equilibrium. Metal surface is to be thoroughly cleaned, and usually the cleaning is done by dipping in concentrated HNO3. So here these are the typical in figure 2.7. You can see typical indicator designs of different types of indicator electrodes. So in addition to the above, where metal electrode is used, an indicator electrode for its own cations, it can be used indirectly. So for this application, it is necessary to saturate the solution under study with the sparingly soluble salt. Like for example, the here we can use silver electrode which is dipped with silver iodide. The reactions involving in these equations are AgI forming Ag plus I minus, then Ag plus E, Ag here combining these two equations and applying Nernst equation, we can find here that E is equal to 0.151 minus 0.059 into log of concentration of I minus. So this type of electrode where silver serves as the indicator electrode for iodide is called as an electrode of the second order because it measures the concentration of the ion that is directly not involved in the process. So then comes the mercury electrodes. Another important second order electrode that is used for the measurement of EDTA and its anion Y4 based on the response of mercury electrode is the stable Hg2 EDTA complex. So the Hapsel reactions can be written in equation 2.35 and for which the E can be calculated from equation 2.36. So for this electrode system, a small concentration of HgY2 minus, it is introduced in the analyte solution. The complex is so stable that the dissociation to form Hg2 plus is very minimal. So the above equation is simplified to the equation 2.37, and where after the this is the value of K, and this electrode is particularly used in complexometric titrations that involve EDTA. Then coming to membrane or ion selective electrode. So there are another category of electrodes. Those are called as membrane or ion selective electrodes. These electrodes preferentially respond to a single chemical species. The potential between the indicator electrode and the reference electrode, it varies as the concentration or activity of that particular species varies. So unlike the inert indicator electrodes, ion selective electrodes, they do not respond to all species. That is why they are called as ion selective electrodes. For example, glass membrane electrode, or that is the glass electrode, is a particular case of ion selective electrode, that these electrodes, they are used in pH meters. And then coming to determination of equilibrium constants. So for electrode potential measurements, we can calculate the numerical values of many equilibrium constant. So here we know the equation that delta G is equal to del G0 plus 2.303 RT log K. So in equilibrium, we know that delta G is equal to 0. So now delta G0, it becomes 2.3 minus 2.3 RT log K, and combining, also we know that delta G0 is equal to minus NFE. When we combine this, we get log K is equal to NFE0 by 2.3303 RT. So which, upon substituting the value of F, R and T, we get that log K is equal to N of E0 cell by 0.591. So the equilibrium constant for any reaction can also be calculated by using the value of E cell in the standard state, and the equation in 2.41, it shows that how we can calculate the equilibrium constant for a reaction. Then coming to potentiometric titrations. So here the potentiometric titration, they generally offer, they are very accurate in nature and they are also very precise. Now here accuracy is increased in comparison to direct potentiometry, is because here the measured potentials, they are used to detect rapid changes. That we, how do we know the change? We look at the equivalence point, and from the equivalence point, even if the reaction is very fast, from the equivalence point we can calculate the changes that is occurring inside the reaction. Potentiometric titrations, they have been used for a different types of systems. Potentiometric endpoint detection, they provide more accurate result than the corresponding method. It is particularly useful for titration of colored or opaque solutions and for detecting the presence of unsuspected species in solution. But one limitation is that it is more time consuming than a titration which is performed with a normal titration. So other than that, potentiometric titrations, they are much more sensitive than normal titrations. So here, if we look here in figure 2.8, you can see this is a typical apparatus for a potentiometric titration method. So the titrant, it is added in large amount. When the endpoint approaches, the increments are made smaller. Then the after that, the time is allowed, for sufficient time is given for achievement of the equilibrium. Now a number of commercial potentiometric titration units, they have been available. So directly we can buy this potentiometric titration units, those are available from the market. So how do we measure the endpoint? So in potentiometric titration, the endpoint is determined by determining the volume at which there is a very drastic change in the potential. So this method can be used for different types of acid base reaction, redox reaction and complex formation reactions. So here, if we see from figure 2.9, these are different the titration curves that we can see, potentiometric titration curves. And once we know the drastic changes that occurring here in such cases, we can find out the, actually locate the equivalence point. So here the potential is measured after the addition of each successive titration. So we keep on adding our titrant, and then with each addition we note down the potential value. So as we keep on potential, well, keep on adding, then we see a large difference. So this equivalent point is determined by dropping vertical line point. So here in figure 2.9b, you can see how we can calculate the different types of the equivalence point from different types of potentiometric titration curve. So in figure 2.9a, you see this is just a very normal typical EMF versus volume plot, but it is very difficult to calculate the equivalence point. That is why, so what we do is we plot a graph of delta E by delta V, that is the first derivative titration curve, that is here shown in figure B, and then at the highest point we drop a perpendicular to the x-axis, and then we can find out the equivalence point. So here delta E by delta B plot is more accurate to calculate the to know the equivalence point for a particular reaction. So here in figure also, the if we have a very complex reaction, so then we can calculate delta E square by delta V square, and from this we can also know the point at which this plot crosses the zero axis. We can know the equivalence point. So this is how the equivalence point can be known from either from the first derivative titration curve or from the second derivative titration curve. So these are some of the titration curves. Then coming to types of potentiometric titrations. So the majority of potentiometric titrations that involve chemical reactions such as neutralization reaction, oxidation reduction reactions, precipitation reactions, and complexation reactions. So these are the four different types of reactions where potentiometric titrations have been involved, and all of these reactions have been discussed here in greater details. So we'll just start with the first, we will start with neutralization reactions. So neutralization reactions, it can be directly written as, we know that Ka is equal to, for that is for acid, it can be weak acid Ha, it can be written as H plus A minus. The pKa is given as this. Then when we do titration of weak acid with a strong base, and then we note that the pK values can directly be read from the titration curves. So then coming to oxidation reduction titrations, the indicator electrodes for oxidation reductions, they are fabricated from platinum, gold, or mercury. Suppose we take a general reaction, then the potent, that is the Nernst equation can be written as E is equal to E0 plus 0.0591 by N into log of A oxidant by A reductant, and using this we can calculate the E of our species. Then precipitation reactions, these are the titrations that involve the precipitation reactions. However, the indicator electrode is mostly the metal which reacts, that is taken. So, and the here theoretical curves for a potentiometric titrations are derived. For example, we can take a silver electrode. The E of Ag is written here. Alternatively, the E of Ag can be also found from this equation in 2.49. Then complex forming titrations, both the metal electrodes and the membrane electrodes can be used to detect endpoint in reactions that involve the formation of a soluble complex. Mostly these complex forming titrations are used for EDTA, and mercury electrode has been used. Then differential titration, differential titrations, they require the use of two identical indicator electrodes. Here in figure 2.11, this is a differential potentiometric titration. It has been shown here. Then automatic titration. So in automatic titrations, they are very much in use today. So two different automatic titrations, they are available. The first type, they give the V versus E, or delta E versus V by V, that is the first derivative plot. In the second type of automatic titrators, the titration is stopped automatically when the potential it reaches a predetermined value, and the volume of reagent, it is read at operators or of our convenience, these titrators, they employ a burette system with a solenoid that is operated, and it makes use of a syringe which is activated by the motor driven screw. So automatic titrations, they are much more in demand in comparison to the conventional titrators. So with this, we finish our part on potentiometry and the different types of potential applications. So this much for today. In tomorrow's class, we'll start with unit 3. Thank you for today.